The frontier this week is less about bigger models and more about getting AI to act reliably in the real world. In robotics, we're seeing a push toward smoother, more precise control without paying the usual latency and jitter tax, while in science, coding agents are being tested against published Nature family results instead of toy benchmarks. The common thread is simple. Can these systems move from impressive demos to trustworthy execution? Keep watching, because the details here expose where current AI is strong, where it still breaks, and what actually closes the gap. Let's explore the first paper, Learning High-Frequency Continuous Action Chunks in Latent Space. Learning high-frequency continuous action chunks in latent space argues that robotic action chunking breaks down at 60 Hz when policies predict directly in action space, producing jitter, quantization error, and boundary stalls. The paper's core idea is to encode 4 8-step high-frequency action chunks with a variational autoencoder, train the policy in a 1-0 dimensional latent space, and decode back to actions at execution time. This consistently improves trajectory, smoothness, and precision across diffusion policy, OpenVLA OFT, and PI 0.5. On real-world contact-rich tasks, peel cucumber, wipe vase, and write board, the latent formulation reduces jerk sharply. For example, OpenVLA OFT on write board drops from 5.238 to 0.558 jerk, and lifts success from 74% to 100%, while diffusion policy on the same task drops from 1.14 to 0.511 jerk. To handle asynchronous inference, the authors add reuse then refine, a training-free method that reuses overlapping executed actions, concatenates them with the new chunk, and refines the result through the VAE. This lowers chunk boundary gaps and reduces execution stalls, especially for PI 0.5, where the asynchronous write board jerk falls from 4.984 to 1.754. The experiments also show that moderate latent compression helps, but overly aggressive compression degrades both precision and smoothness, and the VAE adds only about 2.3 milliseconds of encode-decode overhead. Let's explore the second paper, LightWAM Efficient World Action Models with State Fusion Action Decoding. LightWAM, from Wuhan University and the Shanghai Innovation Institute, rethinks world action models for robot manipulation by separating the expensive parts of video code training from the action decoder. Instead of using a heavy generative policy, it freezes a 1, 2, 1, T, 2, V, 1, 3, B video backbone, adds LoRa plus sparse WAM adapters at layers 8, 16, and 24, and supervises future video prediction in a 2x downsample latent space to cut token cost. For control, it replaces iterative generation with a state fusion action expert that pulls multi-level backbone states through 16 learn queries per layer and predicts action chunks in a single forward pass. On Libero, LightWAM reaches 97.2% average success, with 98.2% on spatial, 99.6% on object, 97.8% on goal, and 93% on long. On RoboTwin 2, it achieves 76.4% average success across 50 tasks without embodied pre-training. The efficiency gains are substantial. Compared with FastWAM, trainable parameters drop from 6, 2B to 0, 44B. Training throughput rises 4.25 times, inference latency falls to 72.03 milliseconds, and peak GPU memory falls to 1 GIB. Ablations show that removing downsampling improves Libero spatial only slightly to 99%, but at much higher costs, while having query capacity from 16 to 8 drops success to 95.4%, confirming that the query bottleneck must still preserve manipulation-relevant visual detail. Let's explore the third paper. NatureBench Can Coding Agents Match the Published SOTA of Nature Family Papers? NatureBench, from Horizon Research, Frontis, AI, and Tsinghua University, asks whether coding agents can actually beat the published state-of-the-art on real Nature family science papers, not just reproduce them. The benchmark contains 90 containerized tasks distilled from about 5,500 papers across 10 Nature family journals and 6 scientific domains, built through the NatureGym pipeline that filters, verifies, and packages each paper into an isolated environment with hidden ground truth and an information firewall. Under a strict web search disabled protocol, 10 frontier agents were tested, including Claude Code with Claude Opus 4.6 and 4.7, OpenAI Codex CLI with GPT-5, 4, and GPT-5, 5, Gemini CLI with Gemini 3.5 Flash, plus DeepSeek V4 Pro Quen 3,7, Max, Kimi Quay, Zes, GLM 5,1, and Minimax M2, 7. The strongest system, Claude Opus 4.7, surpassed the paper-reported SOTA on only 17.8% of tasks and matched it on 47.8%, while the benchmark's validity checks and reproduce mode calibration showed the SOTA anchors were well aligned, with median relative gap near zero on tasks both Claude Opus 4.6 and DeepSeek V4 Pro could reproduce. The main behavioral finding is that agents usually win by methodological translation, most often converting scientific problems into supervised prediction pipelines, which accounted for 45.5% of validated successes, whereas failures are dominated by wrong method choice at 45.1% and insufficient compute budget at 24.4%. That's a wrap on today's AI paper highlights. Thanks for watching.